The problem given in this slide is basically a problem on forced convection, as the velocity is given in the problem, and it is also a internal flow problem. So overall it is a problem on forced convection and internal flow. To solve this problem, we have to find out the properties of fluid flowing through the tube at bulk mean temperature. Here the bulk mean temperature is the bulk temperature, average of bulk temperature at the inlet of the tube, and bulk temperature at the outlet of the tube. So here that value is 30 degrees Celsius, and we have to take the properties of water from the data book at bulk mean temperature. Then calculate Reynolds number, and here the Reynolds number is greater than 2300. The flow is turbulent flow, as it is given that the flow is fully developed, and from the value of Reynolds number we came to an understanding that the flow is turbulent flow. So the suitable formulae, empirical formulae for these conditions is Nusselt number is equal to 0.023, Reynolds number suffix d whole power 0.8, Prandtl number to the power of n. Here the n value is 0.4, as the bulk temperature at the inlet is at the outlet is greater than the bulk temperature at the inlet. So that means fluid is getting heated up. So n value is equal to 0.4. So this correlation, or this empirical formula, is called as Dittus-Boelter's equation. So by applying this correlation, we can find out H value, and here H value is 32,813 watt per meter square Kelvin. Next, by applying energy balance, heat gained by fluid through convection is equal to rate of increase in fluid energy. So Newton's law of cooling, that is H into A into Ts minus bulk mean temperature, is equal to m dot into Cp into bulk mean temperature at the inlet minus bulk mean temperature bulk mean temperature at the outlet minus bulk mean temperature at the inlet. So by applying this formula, so m dot is rho into velocity into cross sectional area. So from this we can find out length of the tube needed. Here the length of the tube is around 23 millimeter. So here it is the formation of boundary layers, both thermal boundary layer and velocity boundary layer in natural convection over a vertical flat plate. You can see the vertical flat plate whose surface is at temperature Ts, and bulk fluid temperature is T infinity, and gravity will be acting downwards against buoyancy forces. The layers near the vertical plate gets heated up, their density decreases, they will move upwards, they will cause buoyancy. I mean, those upward forces are called as buoyancy forces. These buoyancy forces act against gravity. Here you can see two boundary layers. One is thermal boundary layer. Within the thermal boundary layer there is a variation of temperature from surface temperature at y is equal to 0 to free stream bulk fluid temperature near the boundary layer. So the curve is the temperature profile which varies with respect to y direction. So here the y direction is normal to the surface of the vertical plate. Second one, the boundary layer, which is represented in form of dotted line. In that there exists the velocity gradient, and the velocity varies from 0 at the surface to 0 near the velocity boundary layer. In between, the velocity is greater than 0, and and reaches maximum at reaches maximum. Reaches maximum at some place between the surface and boundary layer thickness. Here delta represents thickness of velocity boundary layer, delta T represents the thickness of thermal boundary layer. Now next problem is on free convection. Consider this free convection problem. Here the fluid properties, that means air properties, must be taken at film temperature. Here the film temperature is T wall temperature or T surface temperature plus bulk fluid temperature divided by 2. It is so the film temperature here is 55 degrees Celsius. So to solve this problem, let us consider the orientation of the plate is vertical. The physical dimension of the plate, which is parallel to the natural convection currents upwards, is 0.6 meters. So L is taken as 0.6 meters. Now calculate Grashof number into Prandtl number, that is Rayleigh's number, and the properties have to be taken at film temperature. Now here the Grashof number into Prandtl number is given as 9.499 to 10 power 8, but probably the Prandtl number is not multiplied with Grashof number. That's why the value is little bit different. So you please multiply Prandtl number with Grashof number. You will be getting a different value for Rayleigh's number. Since Rayleigh's number is between 10 power 4 and 10 power 9, from data book you can take the correlation, that is Nusselt number suffix Nusselt number is equal to 0.59 into Rayleigh's number whole to the power of 0.25. Okay, so substitute all the values and find out H value, then apply Newton's law of cooling. Q is equal to HA into Ts minus T infinitum. So find out Q value in watts. Next, the orientation of the plate is horizontal with the hard surface upwards and bottom surface is insulated. Now here we have to find out the length. From data book, the length is given as area by perimeters. Area is 0.6 meter into 0.6 meter divided by perimeter is 2 times that of 0.6 plus 0.6. That will give us the length, and here the length is for horizontal orientation 0.15 meters. Again calculate Grashof number suffix L into Prandtl number, that is Rayleigh's number suffix L, and the only difference is L value. Here the L value is 0.15 meters. Calculate Grashof number into Prandtl number, that is Rayleigh's number suffix L, and so this range is between 8 into 10 power 6 to 10 power 11. So for upper surface heated from the data book, for that for those values of Rayleigh's number, the correlation given is Nusselt number is 0.15 into Rayleigh's number to the power of 0.333. So from this calculate H value, again apply Newton's law of cooling, H into A into Ts minus T infinitum. So find out here the area is 0.6 into 0.6 as the bottom surface is insulated. So find out Q value. Now in horizontal orientation, the second bit is the top surface is insulated and bottom surface is heated up. So for this particular case, from data book, bottom surface heated up, the correlation given is Nusselt number is 0.27 into Grashof number into Prandtl number whole to the power of 0.25. Here also L value is 0.15 meters. So apply that correlation, substitute all the values and find out H value. Here H value is around 3 watt per meter square Kelvin. Now apply Newton's law of cooling. As the top surface is insulated, bottom area of bottom surface is 0.6 meter by 0.6 meter. Substitute all the values, get Q value. Now you can see the heat dissipation in all three cases. So the maximum amount of heat dissipation by natural convection takes place when bottom surface is insulated and hot surface is facing up. Next, the higher rate of heat dissipation by natural convection is when the orientation of the plate is vertical, and the least amount of heat dissipation by natural convection is when the orientation of the plate is horizontal and top surface is insulated and hot surface is facing down. Thank you.